Hello everybody, welcome to another video lecture of Discrete-Time Systems course. In this lecture we will mainly introduce digital control systems, try to understand the concepts and the fundamental picture. Okay, so last semester in GOT course we covered classical control systems where we have a topology something like this. Okay, let's change the color. Okay, so in this topology the most critical part was the feedback part, okay, where we subtract the reference signal from the output. Okay, we have a planned transfer function. Also, it can be in state space form, which is technically a mathematical model of a physical system, such as like mechanical systems, spring dampers, pendulums, or it can be anything that we want to control, such as like heat of a room, chemical process, and stuff like this. And G of C was a continuous time or analog controller that we designed such that the closed-loop system satisfies some of the performance criteria, such as transient performance, robust maintenance metrics such as phase and gain margin, or steady-state performance. Okay, and later on top of this, we analyze different kind of systems, controllers from different kind of aspects, and we also analyzed more complex topologies. But this was the basic idea, right? We analyzed P controllers, PID controllers, and like this. But the most important thing is everything, this, or feedback loop working in continuous time domain, and the controllers are assumed to be analog controllers. Okay, so in all of the world, the fundamental control systems course is taught in like this manner, such as we design analog controllers. But we know that in modern world, the dominant majority of the controllers is not analog. We use digital controllers, digital computers, such that we need to use different tools. Okay, so in this case, we have a plant and we have a continuous time controller. Okay. However, in a digital control framework, we will need different fundamental operators. Even for most basic form, we need more than this. Okay, well, let's look at the big picture of this course. Okay, so let's clean this. Okay, still we have a reference signal. In this case, we assume it to be also analog signal. It doesn't matter. It's not very important. Our output is also continuous because it is the output of an actual plant. We still want to control a physical system. Okay, so it can be a mechanical system, chemical process, a combination of both, or electromechanical systems such as DC motors coupled with like gearboxes, like autonomous cars and something like this. Okay, so the plant is still living in continuous time. So we have a plant, okay, it's a continuous time dynamical system, and we assume that the plant can be modeled with smooth differential equations, or smooth state space equations, or smooth transfer function forms. Okay, so I call it smooth because it works in continuous domain, and in general we assume that its state space dynamics has this form, or we can have a transfer functions and linear system or not. Okay, so this is the basic idea. So we still want to control same plant or similar plant, but in this case we need more thing because our controller is digital. Okay, so it's not a simple analog controller. We can assume it's an analog controller, and we can move forward with that, which is a straightforward approach adopted in industry, but it's not a very good approach. We need to be more concrete and better. Okay, so we still have a feedback term here, and as you can see, feedback term is still in continuous time domain. It doesn't have to be, and we will cover different kind of feedback operations. But now we have a control block, digital control block, which is composed of three main components. Here it says ADC, this is mu P, and this is DAC. So what is that? Let's start with the first one, analog to digital controller. Okay, since our plant or continuous time system lives in continuous time domain, since our computer or controller works in digital domain, we need an analog to digital controller. Okay, no, converter. Sorry about that. It's not controller. So it can be also controller, but this is converter. Okay, let's change the color. Converter. Okay. In an ideal case, this will be continuous time to discrete time controller, but the physical name, the device name is analog to digital controller. There are different type of analog to digital controllers. There are different kind of linearities and nonlinearities associated with these devices, but the basic idea is this operator takes an analog signal or continuous time signals and produces a discrete time signal. Okay, this is the basic idea. The third block that you can see in this picture is a microprocessor or a controller, computer microprocessor, which basically computes the desired control actions. Okay, so takes the signals that comes from the analog digital controller. For example, these are the sample signals. As you can see, we sample E of t. Analog to digital converter converts it to a discrete time signal, E of k. Now k is a sample time. I will talk about this. And microcontroller computes the control actions and produces a set of discrete time control outputs or inputs. Okay, so U of k is control input. So in this course, we assume that microprocessor and controller has a real-time, hard real-time operating system, and it has a hard real-time clock. Okay, so I will talk about this in a minute. And fourth block is, yes, our microcontroller produced discrete time control actions, but our system is a physical system. We need to convert them to voltage, currents, torques, or that are physical. So what we need a digital to analog converter. Now we need to take digital discrete time signals, convert them into real physical quantities such as voltage, current, force, torque, or anything that is accepted by the Laplace transfer function. Okay, so the most critical thing in this course is we assume that this whole block, so let's clean them. Okay, so do we have an okay, object trace is better. Okay, this is this whole digital block which is here. Okay, runs under a real-time operating system and ADC microcontroller DEC blocks are synchronous with a real-time clock. Okay, so it's important because when they are not synchronous, when your software infrastructure or embedded system is doesn't work in real time, your computations, control actions, estimation actions will be much harder. Okay, so the embedded systems programmers that works with control engineers generally tries to achieve these real-time specifications in your controllers such that your completed control actions works in the real system as expected, for example, with respect to your theoretical or simulation computations. Okay, so this is important, and in this course we assume that all of the ADC, DAC, microcontroller samplers, control actions are real time and they're synchronous. Okay, it's important because especially the chip controllers that you will use, for example, in your design course, will not work this like synchronously. The clock may not be real time. You may have synchronous, like asynchronous signals coming from different kind of sensors. You need to deal with these kind of issues, which will generate noise and uncertainty. Okay, but in those course, we assume that everything is synchronous. Okay, this is good. So what we can do is let's start with the analog to digital block. Okay. So as you can see, the main function of ADC is it takes an E of t as the input, which is a continuous time signal, and produces A of k, where E of t looks like this and E of k looks like this. Okay. Something like this. Okay, so what is the function? Okay, so technically, this mathematically, E of k is equal to E of kt, where k is an element of integers. We assume it is like a unilateral. And t, which is of course greater than 0, is at the sampling time of the system. And we know that t is equal to 1 over f. So it's the sampling frequency. Okay, and t is the sampling period. And we assume that t is constant for the whole system and it is fixed. Okay, so in a control area there is research when t is not constant, it is changing, it's stochastic, or sometimes we even try to change t such that we, for example, consume energy. We need to deal with the combination products and like this. But in this course, t is constant. It's called sampling time, and of course, it is greater than 0. Okay, so this is the main function of the analog digital controller. Just take the signal, sample it, and convert it to discrete time signal. Okay, so this is the basic idea. Okay, so the outputs are defined. Let's specify instance defined by real time. Okay, good. So the basic idea in this sampling case, and it's kind of important. As you can see, we miss information here. Okay, so the sampling inherently like loses information. It's a continuous time signal to discrete time signal, and we lose information. Okay, so in this course, it's not as critical as that you cover in the digital signal processing course, because we want to control the system, but still you lose some information, and it's important. Okay, good. So, and then, okay, we know that we have a discrete time signal. Our microcontroller produces a discrete time output. For this reason, our microcontroller mu, or let's can say g of cz, is a pure discrete time system. Okay, u of k. Okay, e of k is the input, it's the discrete time, and u of k is the output. Okay, so it's possible that your digital controller or this block doesn't care what's happening in the real world. Okay, because for this guy, for this block, everything is purely discrete. Discrete time input, discrete time output. Okay, and we model it using a discrete time state space representation, or discrete time transfer function, which is defined by the Z transform equation. Okay, so we know that, and now what we have is the DAC. Okay, so let's clean everything. So what is DAC? DAC is a digital to analog converter. Okay, so if your system static, it's easy, right? Okay, you just get an input. For example, your controller says that like apply this voltage, and let's say this voltage is like 5 volts. It's digital and it converts into real volts. But in dynamical systems, what is DAC? Okay, so let's look at the input. This is DAC. This is digital to analog converter. As you can see, input is a discrete time sequence. Okay, let's make it simple. Like this goes to 0. And these are indices 2, 3, 4, 5. Okay, so these are discrete time. We don't even know this block what is 1, what is 2. Okay, so first thing that is required to make a real digital analog controller block is knowing the time in the real world. You need to convert these times, these instances, to real times. Okay, so this is 0. So this goes like this, this goes like this, this goes like this. So what are they? Okay, so since this is k, since this is t, these instances are associated with 0, 1 times k, 2 times k. So technically, you take k, you map it to k times t. This is your t hat. Okay, good. So we can scale this. Now I'm talking about both mathematics and the physics. It's kind of complicated, but it's like this. So I know this. I know that these variables are associated with this, right? Okay. But I need to fill in the gaps, right? Because this is a discrete time signal. Output of digital analog controller is a continuous time signal. How I can fill in the gaps? Okay, so it's important. And you should be careful that this digital analog controller block is a causal system. Okay, so it is causal. It cannot use future information. So in order to capture what's happening in between these two, it cannot use information that is forward in time. Okay, so the most useful, dominantly used digital controller uses the concept of zero order halt. What is zero order halt? Is this? Okay, so you read the value of the discrete time signal at 0, and you keep it constant until you hit a naive sample. Okay, now I have a naive sample. Okay, so sorry for that. It should be 0. So let's clean this. Okay, oh, sorry for that. Okay, this is like this. So let's make it. Okay, so this is 0. Now I have a naive sample. This is like this. Now it is like this. This is like this. It's like this, and it goes like this. Okay, so as you can see here and here, zero order halts looks like a stochastic ladder, right? Or piecewise constant square wave function. Okay, so it's constant in between two sampling instants, but the variable is changing when you get a naive sample or naive information from the microcontroller. Okay, so from 0 to 1, for example, it is t is equal to 1 second. It is constant. At t is equal to 1, you get a naive value from the microcontroller. You change the output. It goes like this. This is important because in dynamical systems, of course, your output is changing. You are constantly producing voltage values, force values, or other kind of control actions. And when any control action comes to your system, you change your output. Okay, so this is the output of the controller, and this is called a zero order halt operation. Okay, so we will slightly cover first order halt. I will just mention it. I will not cover in detail because in microcontrol algorithms, zero order halt is dominantly used almost in any system, because in order to apply higher order halt operators such as first or second order halt, first it needs significant hardware improvement in their system, and second thing is it really doesn't bring anything useful. Okay, because applying this is cheap, easy, and instead of putting your effort to implement first order halt or other kind of halt operators, you just try to increase your sampling time, which is much better than just kind of approximating this function a little bit better to reflect the continuous time action. Okay, so this is the basic idea of the zero order halt operator. Okay, so this is the big picture. Let me clean everything, and I will briefly explain the details, and then we will briefly talk about the sampling. Okay, and I need to show that. Okay, so I forget. Okay, so this is this. So when your input u of k, okay, how you can compute u of t, right? So you can say that we know that u kt is equal to k times t. No, okay, so for that, okay, well, let's show them uk. Okay, so we know that, but this is at this sampling instance. I need to fill in the gaps. It's very simple. U of t is technically equal to u of k under zero order halt, right? And for t element of kt to k plus 1 t. Okay. So this is technically everything that operator performs in a mathematical domain. Okay, so u of t is piecewise constant function, and this piecewise constant comes from between two sampling instants. Okay, from k2 to k plus 1 t, it's constant. From k plus 1 t to k plus 2 t, it's constant, but it's different. Okay, so it is a ladder-like structure. Okay, so this is the DAC operator. So what we covered is, we covered the basics of ADC, microcontroller, digital controller, plant, and whole digital control system block. Now let's talk about the ADC a little bit more, which is important in our lecture. Okay, good. Now, what I do is, before going into details, I simplified my structure, as you can see. So this is the actual big picture, but now this is the big picture of this course. Now it's a discrete time course, and instead of using like ADCs, other kind of things, we will use mathematical terms. So GP of S is the transfer function of the plant. So this is plant. Okay. GC of Z, now microcontroller is a discrete time dynamical system. It's a transfer function in Z domain, or it can be state space in discrete time domain. Okay. So controller. We have a zero order hold operator. We still write it as zero order hold. So instead of digital to analog converter term, we will use zero order hold, or in a different framework, it can be first order hold. It's zero order hold. So we have R of t, which is the reference signal, and instead of ADC, we use a sampler. Okay, what is sampler? Sampler is the idealization of analog to digital converter. Okay, so what's the function of sampler is, it has a time, sampling time t, as you can see it is assumed to be constant, input signal is continuous, output is discrete, okay, E of k. Controller GC of Z, here as you can see, input is discrete, output is discrete. Zero order hold, input is discrete, output is continuous, GP continuous and continuous. Okay, so the sampler and zero order hold are important because they are the interface between two worlds. One world is S domain or continuous time domain. The other domain is Z domain and discrete time domain. Okay, they're different worlds. And you can think the sampler and zero order hold are the gates or interfaces where you can combine between two separate worlds. They're completely different. They're like mathematics, the actions, details are different from each other, but because of the sampling and zero order hold operator, we can have a concrete mathematical structure such that we can design the whole digital control system. Okay, we will talk about zero order hold later. Today I will talk about sampling and sampler a little bit. Okay, good. So let's show something else. Okay, this is sampler. Okay, so here I illustrate two different ideal samplers. Okay, and I will cover both of them in this course. They're like similar, but there are some differences. But difference is more like in their notion and notation. Okay, so first one is an ideal continuous time to discrete time sampler. Okay, so what is that? Input is continuous time, output is discrete time, and we know that E of k is equal to E of kt. In general, understanding this operation is very easy, right? Okay, so in order to compute a discrete time signal, what I do is, to compute E of k, I just simply multiply k with capital T, which is sampling time. I look at the value of E, continuous time, E in this domain, and it's my discrete time signal. Okay, so and it's ideal, right? It's not actual because discrete time signals, even analog signals, are kind of abstraction of the physical world or computer world. Okay, so here I have a different sampler, which we call impulse sampler. Okay, so this is more abstract than this. So in this case, what I do is, as you can see, my input is continuous. My output is still lives in continuous time domain, T domain. So it's not different. Okay, this is T, this is T. So I'm not changing my T in the impulse sampler. Okay, so it's the most important thing. So in the impulse sampler, I don't change my domain. I just do, instead of using E of t, I model E of t, or I divide E of t into set of impulse functions. So as you can see, these are impulse functions because they are arrows. Okay, so what we do is, in the impulse sampler, converts E of t into an impulse train function. Okay, so this is continuous time signal, and it is now a continuous time signal, but now my signal is just composed of a bunch of impulses in the time domain. So we know that impulse function is abstract, it's not real, it can't be real. So we say that its duration is 0, but its strength is constant, so its amplitude infinity. Okay, so it's abstraction, but we previously know from signal systems course is that impulse function, impulse trains are very useful to model some systems or analyze dynamical systems, signals, signal system theories. So we will use the same thing here. Okay, so how we can model this is using a very simple, so let's clean this, multiplication operation. Okay, so what is that? So E of t is the continuous time signal, and we model this switch with a multiplication block. This is multiplication, where we multiply two signals. One is the input signal and the other one impulse train. Okay, so this is the impulse train function with a sampling time of t. So what is this? We say that it is sum sigma t minus kt. Okay, so t is equal to 0. This is equal to sigma t or delta t. Sorry for that. So we know that delta t is equal to this, right? And strength is equal to 1. Okay, very good. When k is equal to, so let's 1, this is sigma t minus kt. Okay, and let's assume that t is equal to 1. So let's simplify it. T is equal to 1. So sigma t minus 1. So this is here. We sum them, but they're in different positions. So 0, 1, 2, 3. As you can see, this is impulse train function. Okay, so I multiply two signals. Okay, what is important here is that, so this operation, multiplication of t signals, we haven't covered it throughout the class because it is inherent and kind of nonlinear or time varying operation. Okay, so multiplication of a signal with a different signal, even if you know it, it's not a linear operation, or it is time dependent. Okay, so we make it time dependent. So output of this depends on time, right? When you apply E of t, if you shift E of t a little bit, you may get a different result or same result. Okay, good. So here, because of this, signal is time dependent. When you add a sampler to your system becomes automatically a time varying system if you still live in the continuous time domain. Okay, so this is the basic idea. This is my impulse train. Let's change the color. Okay, now what I do is, this is my signal. Let's draw my original signal. Original signal is here. Let's make it like this. Okay, something like this. So if I multiply red with blue, what I obtain is, so multiplication of impulse with a signal is what? If it's a single impulse, everything is 0 except at your impulse time where you apply your impulse, you get the value of this as your strength, and it will be a impulse train again. So if I follow this logic, this is my, okay, so this is bad. So let's use color. If I multiply these two signals, I obtain a different impulse train where the weights or strengths are obtained from my original E of t, but the location of impulses is obtained from my impulse train function. Okay, so important thing is here, at this point, my system, my signal is still continuous. It is somewhat the analog to analog conversion, but my analog signal is fictitious impulse train, which looks like a digital signal. So impulse sampler is somewhere lives between an analog and digital domain. Okay, later what I can do is, I can use a fictitious impulse train to DT sequence converter to obtain a discrete time signal like this, such that I will model an ideal C to the DT sampler using an intermediate impulse train block. Okay, so this is the function of impulse train. Okay, I think the idea is very simple. Let's analyze this a little bit mathematically. Okay, so do we have x? Okay, so let's assume that my input signal is x of t, not e of t. Okay, let's change this. Let's x of t. My input signal is of t. Okay, so I feed impulse x of t to an ideal sampler, and I obtain x star of t. Okay, so what is x star of t? Is multiplication of two signals. X of t times my impulse train, sigma tt, let's look like this. Okay, x star of t is equal to x of t times k is, okay, so let's get there, okay, delta, it's t minus k capital T, okay, so I just put x of t inside. If I do that, what I obtain is this, from k is 0 to infinity, x of k capital T times delta k minus, not t minus, okay, let's change that, okay, t minus kt, okay, so this is good. I think everything nice. And okay, so what is this? X kt. What I can do is, I already know that x k capital T is equal to xk. Okay, as you can see, even if you use impulse sampler, if you look at the output, k is equal to 0 to infinity, x of k times sigma t minus kt. Okay, so overall, this signal is continuous. Okay, but all of the information in the signal is stored in this discrete time sequence. Okay, so impulse rate doesn't leave the continuous time world, but still stores the information that is required for the discrete time domain. Okay, so it's somewhere in between. Okay, good. So let's open it a little bit. Okay, so let's choose that. Let's clean it. Okay. So object razor. Okay, this is good. I use the object razor. Okay. So let's change this. Okay, so what is x star of t? X star of t. Okay, good. So let's analyze this a little bit. Let's open it. Instead of summation, just write it separately. So what is this? When k is equal to 0, this is equal to x0, right? Sigma t, delta t. Or I can write the same thing as x0 sigma t. Okay, everything's correct. So x1 or x bracket 1 times sigma t minus capital T. Okay, so this is not 1, this is capital T, sorry for that, but this is 1. Okay, sigma t minus t, okay, plus when k is equal to 2, this is x2t plus or x2 sigma t minus 2t sigma t minus 2t, and it goes like this until infinity. Okay, so if you open it, you can see the similarities between discrete time and continuous time. Okay, good. Nice. Okay, so we know x star of t. It's good. I like it. I hope you like it. And you will see that it will be useful for modeling digital control system. And let's do something really weird. Okay, something I think you haven't taught much. Okay, so let's clean it. So let's rewrite x star of t here. X star of t is equal to summation x equal to 0 to infinity. Okay, x kt times sigma delta t minus kt. Sorry, I just copied it. Or it can be k equal to 0 to infinity x of k delta t minus kt. Okay, so what I will do is, since I claim that x star of t is a continuous time signal, what I can do is I can take its Laplace transform, right? Okay, because it's continuous time, it's not discrete. It looks like discrete, but we have time. If I have time, I can take Laplace transform. Okay, so Laplace transform of x star of t. Okay, which is weird, right? I think it's very weird. Okay, Laplace transform of k is 0 to infinity xkt times delta t minus kt. Okay, so what is Laplace transform? It's an operation, it's a linear operation, it's important, and it's uses the variable t. Anything that doesn't depend on t, small t, can be just brought out from the Laplace transformation, such as the summation, this x times k of t. This is the only function that I need to take the Laplace transform, right? Okay, because of the linearity. So this is simply equal to k is equal to 0 to infinity x kt times the Laplace transform of delta function t minus k t. I think it's good, right? It's very simple. Okay, so I think you may remember the Laplace transform of delta function, but just use the definition of Laplace transform. Okay, we can drive very quickly. K is equal to 0 to infinity x kt times what is the Laplace transform? If you remember, we have an integral. Okay, let's assume it starts from 0 because it's a unilateral Laplace transform. And we know that k and t are both greater than 0. Okay, sigma t minus kt e to the power minus st dt. Okay, good. So this is same. Just write it. K is equal to 0 to infinity x kt, and what we need to do is we need to compute this integral. Okay, so it's an integral. So we multiply two functions, take the integral. But this is delta function. What's a delta function? Delta function has a value at some point. Okay, it is infinite, but it's a strength. But otherwise, it is just 0. So what I do is, as you know, I just obtain the value of this function, which is exponential. It's complex exponential when t is equal to kt, right? So if I do that, this is equal to times e to power minus s k t. Okay, so x Laplace transform x star of s is equal to, so let's change the color. K is equal to 0 to infinity x k of t times e to power minus s k t. Okay, so it doesn't look like a nice Laplace transform, right? I think so. So it really doesn't look like something useful or something concrete. Okay, so I can also change it 0 to infinity x of k. I can write this, right? Because I know that x k of t in continuous domain is equal to x k e to the power minus s k t. I have complex exponential. I don't know what it is. Okay, and I have infinite many of them, not one. For k is equal to 1, 2, 3 until the infinite. Okay, now we will make a trick. And this trick will be very nice. Okay, so I don't like s at this point. Okay, because I have k. So this is discrete signal. This is not a discrete signal. So here it is Laplace transform of something, but it looks like a discrete signal. So what I want to change is, I don't want to use s. Okay, so I want to use z, which is something familiar. And I assume that z is equal to e to the power ts. So what is this? T is the sampling time. Okay, s is the complex exponential. It looks nice, right? Or I can write s as equal to 1 over t ln z. I can write that, right? Okay, so if I use this transformation, so what is this? Okay, I think it becomes very nice because I have e to the ts. So I need to separate e minus k. So x star of s is somewhat, if I replace s with 1 over t ln z, is equal to k is 0 to infinity x of k times z to the power minus k. Okay, so this is nice, right? Because I find this. So what is that? I think most of you remember that this is indeed the z transform of the sampled signal. Okay, I think it's now nice because let's change it. here. Okay, so x, we found x star of s, Laplace transform of x star, okay, t, which is equal to the Laplace transform of x star of t is equal to, not equal to, so if you change s with 1 over t ln z is equal to x of z, which is the z transform of x of k. Okay, so since start Laplace transform, so start signal x star of t lives somewhere in between continuous and discrete domain, it carries information from the both worlds. So if you take the Laplace transform of x star of s, okay, which is the basic x star of s, t, so x star of s carries information both in Laplace domain, or if you make the necessary change of variables, also in the discrete domain. Now this is very powerful for us, which says that maybe we can do our computations analysis in Laplace or t domain as much as possible. We can even design controllers in S domain, then we can emulate them in the Z domain by using this simple change of coordinates, right? Okay, so x of z, and we know that this is equal to k is equal to 0 to infinity xk z to power minus k. Okay, good. So the take-home messages, let's go to the beginning. We started what we learned from GO2 class. Then in this lecture, we covered the fundamental block diagram structure in digital control systems, where we have a plant, which is same in our classical feedback systems course, but now our controller is a digital controller or a whole control system, which is composed of analytical digital controller, microcontroller, and digital controller. Okay. And later we kind of learned that, so we can model the controller using a Discrete-Time transfer function. Analog to digital analog controller is a zero-order horizontal block. Our sampler converts continuous time signals into discrete time signal, which is the modeling of the analog to the digital control block. And then what we did is we covered two different sampling ideas. One is simple ideal C to DT sampler, converts the continuous time signal into discrete time signal. And then we did a crazy thing. Instead of sampling the signal into a discrete time domain, we sample it but still kept the signal in the continuous time domain using impulse train concept. And finally, we showed that here Laplace transform of this impulse train representation of this sample signal is technically equal to the Z transform of this sample discrete time signal if you make the necessary change of variables. Okay, that's all I want to talk about today. In the next lecture, I will go back to our knowledge on Z transform. I will cover the basic Z transform properties and the Z transform of the basic functions.